Hello, and welcome to today's session on confidence intervals and effect size. As always, before we begin, please make sure that you print the PowerPoint lecture notes and that you have them in front of you so that you can take notes along the way. Today we'll start out by talking about a new idea of confidence intervals, and we'll try to relate this to something that we've talked about previously called the standard error of the mean, which is related to the standard deviation. Having set the stage that way, we'll move on to something called effect size, and we'll learn too about something called meta-analysis. And then finally, we'll close with some thoughts about independent group designs. So to begin, let's just remind ourselves of the research cycle. In the science of psychology, we frequently talk about investigating scientifically behaviors, thoughts, and feelings, and these are the real-world phenomena that our field is interested in. We typically pick one of these real-world phenomena, and we abstract from that using operational definitions and using sampling to come up with something that's manageable, some kind of research representation. And then we use any one of three different kinds of methods. We might use observational methods, survey methods, or experimental methods. Experimental methods are shown here in red because we've recently been talking a lot about those, and we'll end with some experimental methods as well in this presentation today. But today we're really going to be focusing on some data analytic techniques. That is, after we've used any of these methods, including experimental methods, we'll have some research results that will need to be analyzed. And we'll be talking about confidence intervals and standard errors of the mean and other ideas related to data analysis that we hope will give us some research conclusions that will generalize back to the real world. Okay, so let's begin with confidence intervals, also known as how big is your error bar. And we'll start with a familiar picture. Here, we can say that we've seen these pictures before, and we're going to try to begin to understand confidence intervals by using pictures first, because a picture is worth 1,000 p-values. I hope you'll say that with me. Can we all say it together? A picture is worth 1,000 p-values. There you go. Okay. So we've asked this before, which graph makes a more convincing case for drug X, and why do you choose the answer that you do? Just to remind you, what we concluded was in each of the two graphs we have a difference between the drug and the placebo of 3 units. There's a 3-unit difference on the right and a 3-unit difference on the left. We've also talked about the importance of context, where variability is the context. And what we can say is that we have a much smaller variability here on your right than we do on your left. And we can use these error bars to reflect different kinds of dispersion. In this slide, what we're showing is that we might choose to have the error bars reflect the range. It might be that the lower end of the error bar corresponds to the minimum score. It might be that the higher end corresponds to the maximum score. That would be one way to use the error bars. It might be that we use not just the max and the min, but instead something like the interquartile range. And an example here would be the very popular college rankings, where it is frequently the case that the rankings will report the 25th percentile and the 75th percentile for that particular college's scores on an SAT or ACT. Okay, so these can reflect a different kind of dispersion. It can be the actual range, it can be the interquartile range, it can be the standard deviation. And this is the one that you and I are most familiar with. Remember, please, that the standard deviation is the average extent to which a score departs from the mean. And typically, when we're creating graphs, we go up to the mean, and then beyond that, we create an upward error bar. We go up by 1 standard deviation and down by 1 standard deviation. There's a near cousin to the standard deviation that we've seen before, the standard error of the mean. And you might pause just for a moment and see if you can recall the definition for the standard error of the mean, at least its computation, which is fairly simple. If you're not able to recall that right now, you shouldn't feel bad. It's been a little while since we've talked about the standard error, and we'll come back to the computation in just a moment. But the point here in this graph is that this is yet another type of dispersion that we can show graphically. As always, we go up to the mean, and we might go up by 1 standard error and down by 1 standard error, so we can have the error bars reflecting different kinds of dispersion. Okay? The new type that we're going to be learning today is called a confidence interval. And we'll be saying a lot about what confidence intervals are. Confidence intervals correspond to particular so-called confidence levels. And the two confidence levels that we'll be talking about would be a 95% confidence level and a 99% confidence level. Just to set the stage for those, the 95 and 99% confidence levels correspond to the alpha levels that we typically test. Most frequently we use 0.05, and that corresponds to the 95% confidence level. Occasionally we use 0.01, and that would correspond to the 99% confidence level. As you might imagine, these numbers are complementary. 5, and 95 are going to add up to 100. Or if we think in terms of decimals, they would add up to 1. And 0.99 and 0.01 would add up to 1 as well. So we can use confidence intervals as our measure of dispersion, and we can show them graphically by these error bars. A picture will say 1,000 words. Let's remind ourselves of what the standard error is. This is sometimes called just the standard error. Other times it's called more fully the standard error of the mean, and you might even see that in some science literature. You'll see SEM for standard error of the mean. And this is the standard deviation of the distribution of means, or the DOM. So there's a new piece of terminology there. The distribution of means. We haven't seen that one before. I wonder if we can all say that together. Distribution of means, DOM. All right, I knew you could say that with me. Okay, let's see if we can try to understand what the standard error is by first contrasting it with something a little bit more conceptually familiar to us, and that's the standard deviation. The standard deviation describes the average extent to which a raw score, that's a single score that we might make or might have in our study, the average extent to which that score deviates from the mean of the distribution of raw scores. So we're comparing a raw score to a distribution of raw scores, okay, and looking at the standard deviation. Right? The standard error describes the average extent to which a sample mean, that's the mean of one sample, deviates from the mean of a distribution of means, and that's our DOM, the distribution of means. Okay? So let's see if we can unpack that just a little bit. I think I'll give you this example. Imagine that we want to compare the size of an apple to a distribution of apples. Okay? We would do that by figuring out, for example, what is the average extent to which the apples are differing from each other in size. And it might be that we have a particular apple that's pretty close to the mean. It might be a little bit smaller than the mean size. It might be a little bit larger than the mean size. But the idea there is that we would compare a specific apple to a distribution of apples. If we had a different and larger kind of fruit, maybe something like watermelon, we could compare a given watermelon to a distribution of watermelons. But that would be the kind of context that we'd like to use. We wouldn't want to compare a watermelon to a distribution of apples, and we wouldn't want to understand how the apple is sized relative to a distribution of watermelons. We want to make an apples to apples kinds of comparison, and a watermelon to watermelon kind of a comparison. As you'll see, we'll also want to do this with raw scores versus sample means. We'll want to compare a raw score to a distribution of raw scores, and we'll want to compare a sample mean to a distribution of means. Okay? So, see if we can now get a few pictures on this. There are 3 different kinds of distributions that are going to be relevant for today's conversation. Some of these are very familiar to us. One of them is brand new. The distribution of populations of individuals. Okay, that's fairly familiar to us. We've talked about that before. We might use the example of trying to estimate the heights of students on campus. And we could get every student on campus, we could measure their height, and we'd have the full population with some folks very, very tall, others very short, but a lot of them at more intermediate levels of height. The next kind of distribution that we can have is what we're more likely to have in any given study, and that's the distribution of a sample. So instead of measuring all 2,000 students on a college campus, we might instead measure something like 20. That is a relatively manageable sample. And we might have each of those individuals in our Excel spreadsheet. Each one takes up one row. And after we have 20 of those data points, we then take an average, and then we have that sample's mean. What we then do is maybe create a distribution of means. And this is actually a distribution of sample means. So we would do this exercise of bringing in 20 people and getting one mean, and we'll hang on to that datum just for a moment. We let those 20 people go back into the population, and we pull in another sample, again of exactly 20 people, and we get another sample mean. We now have 2 sample means. Okay? And they're probably similar to each other, but not exactly the same. There's some random variability between those 2. We let the second sample go. We bring in a third sample of 20 people. Now we have 3 sample means, and we can keep on doing this to get a 4th sample mean, a 5th sample mean, and on and on and on. After a while, we can take all of these sample means and put them into a distribution of means. Okay? So as we said before, we want to be able to compare apples to apples, watermelons to watermelons, raw scores to raw scores, and means to means. Okay? So we'll have a distribution of means in which to do that. Let's give you now a critical thinking question. Why is the distribution of means here so skinny? We'll let you stop the video and think that one through. Okay, welcome back. Let's talk about a few main points on the distribution of means, or the DOM. And we can ask this question, why would we want to use the standard deviation of the distribution of means? And the answer is so we can put a mean into its context. As we've been talking about in our earlier examples, we want to be able to contextualize the items that we might be analyzing in our research study. So this is similar to the rationale for knowing the standard deviation of a distribution of raw scores. Whether we have a raw score or a mean, we want some context. Again, a raw score gets compared to a distribution of raw scores. A particular mean would be most appropriately compared to a distribution of means, not to a distribution of raw scores. That's a subtle idea. A lot of students struggle with that. I hope you can think that one through and make a comment to yourself about the distribution of means as to whether that's clear or whether you'd like greater clarification in the classroom. Okay, let's do an example or two. Your new drug is given to a sample of depressed patients, and subsequently the sample's mean mood score is 25, whereas the mean of the population of all depressed patients is 20. So this sounds like this might be good news. Your drug might be elevating mood, okay, from 20 to 25. Did our drug have a significant effect, a statistically significant effect? And as is often the case in science, the answer is it depends. If the distribution of means, or the DOM, has a standard deviation of 10 units, then our sample is not so different from the DOM mean. Our drug isn't so special. Well, let's see if we can understand that. Remember that the population has a mean of 20. If we're allowing for a standard deviation of 10 units on that, then we could easily find scores up to 30 and down to 10. It's 20 plus or minus 10. In that kind of a context, the score that you and I have is 25 is not that different. It's within one standard deviation. On the other hand, let's go to this example. If the DOM has a standard deviation of just 1 unit, then our sample mean is very different from the distribution of means. Our drug is very hot stuff. Okay, so again, we start out with a mean of 20, and we go up by 1 and down by 1, so we're swinging up to 21 and down to 19. Our sample had a mean of 25. Okay, now that's very interesting. If we have a mean of 25, we're actually 5 standard deviations away from the overall mean of 20, the distribution of means central point of 20. And that's really quite a bit different. Okay, so the standard deviation is the standard error is the standard deviation of the distribution of means. And that is a confusing concept for some students. But hopefully you're already familiar with the idea of a standard deviation. And now we're just going to create a special word called the standard error. And we're going to reserve that for this very special distribution that we call the distribution of means. We can estimate the standard deviation of the distribution of means from a sample. To do this, and here's our familiar equation, we start out with the standard deviation of the sample. And we divide that by the square root of n, where n is the number of people that we have in our sample. So the standard error, computationally, is equal to the standard deviation of our sample divided by the square root of the number of people that, or participants that we have in that sample. And I hope that you'll memorize this formula. Some of you already have done that. Okay. All right, why don't I ask you to stop the video now and make a note of what has been clear to this point and what remains unclear. And then we'll proceed to try to connect the idea of the standard error to our new topic of confidence intervals. Okay, welcome back. All right, so let's define the confidence interval as a range of values assumed with a specified degree of confidence, sometimes called a level of confidence, to include a population parameter. And usually the population parameter of interest is going to be the mean. So we're going to learn this new measure of dispersion. We have several of them already. We've talked about the range. We've talked about the interquartile range. We talked about the standard deviation. And we reminded ourselves today about the standard error. And now we have one more measure of dispersion called the confidence interval. And here are a couple of examples. We might be, say, 95% confident that the mean height in our classroom is in the range between 5 feet and 7 inches and 5 feet 9 inches. So we could make a point estimate. We could say that we believe that the height in our room is 5'8", and that would be a particular point. But instead of having a point estimate that's a single number, we could instead have an interval estimate. We can say that we believe that we're 95% confident that the actual mean might be, we can't quite say the point, but it's in the range of 5.7 to 5.9. Okay? We might be 95% confident about that. Or we might choose to use a different level of confidence, like the 99% confidence level. We might be, say, 99% confident that the mean height in our classroom is in the range between 5.6 and 5.10. Again, it's an interval estimate, and we're saying that the mean of interest is landing somewhere in that interval, and we're, in this case, 99% confident that the actual mean falls somewhere between that lower bound and that upper bound. Okay? All right, so here's a critical thinking question. Why is the 99% confidence interval, which is 5.6 to 5.10, why is that wider than the 95% confidence interval, which is 5.7 to 5.9? We'll let you stop the video and think that one through. Okay, why don't we move on, and we'll talk a little bit about how we compute these with an upper bound and a lower bound. So each confidence interval is going to have an upper bound, and that would be the top part of our error bar, and a lower bound. That would be the lower portion of our error bar. The upper bound depends on the mean, a standard error, and the confidence level, which would be the 95% confidence level typically. Occasionally we might use a 99% confidence level. This is true equally for the upper and lower bounds. These are the three pieces of information that we're going to need to get started. Okay, so the confidence level is determined by the critical value of t, the number to beat. So let's go ahead and put that all together. If we want a 95% confidence interval, we'll need to find a t critical value at the alpha level equaling 0.05. So let me pause here for a moment and make a connection to something that we've done in Excel a couple of different times. We've used critical values before inside of Excel. For example, when we talked about the z-scores, we talked about the normal distribution. And we can use Excel's norms inv function, the inverse function for the normal standard curve, to obtain the critical value of z. And then we moved on to the chi-square distribution, and we used inside of Excel equals chi-inv, or the inverse function for the chi-square distribution, in order to find the critical value. So the nice thing about these inv functions in Excel is they give us the critical value, whether we're talking about a z coming from the normal curve, or a chi-square coming from the chi-square distribution. Here, we're going to be using the t distribution, and we'll use its inverse function, so equals t-inv, and that will give us the critical value for computing our 95% confidence interval. We can also compute the 99% confidence interval. We'll need to now use the t critical value at alpha equals 0.01 rather than alpha equaling 0.05. So these numbers will always be complementary. 0.05 and 0.95 will add to 1. 0.01 and 0.99, or 99%, will add to 1 as well. Okay, so here's the upper bound and lower bound, and I hope you will memorize these formulas, please. We'll always start out by beginning with the mean, and that's a fairly common place to put the central tendency on our graph at the mean, and then we'll go up by some amount or down by some amount. That amount depends on the standard error, as we've computed recently, and also this t-crit value, which, as we've just said, will come out of the equals t-in function inside of Excel. That product will be added to the mean, and we'll go up by that amount when we're creating our graphs, or we can take that same amount and go down from the mean to get the lower bound on our graphs. Okay, let's see if we can do a practice item. And you might want to have Excel up and handy, so if you need to stop the video now to make Excel handy for you, please feel free to do that. Okay. So assume that a sample in your experiment has the following features. The mean is equal to 10. So on our graph, we're going to draw the column all the way up to 10. And now we need to put some error bars. And the question is, how high should those error bars go? We'll see if we can get the 95% confidence interval. Here's some information that we have. The mean equals 10. The standard deviation is equal to 8. And that again pertains to raw scores, the average extent to which the raw scores are differing from each other. Let's say that we have a sample of 16, so n equals 16, and we have 15 degrees of freedom. If we were to use the t-in function to determine the critical value at the 0.05 alpha level, assuming that we have 15 degrees of freedom, that value would turn out to be 2.13. So we want to now compute the 95% confidence interval, and just to remind you, here's that formula. So you're going to use this formula to get the upper bound and lower bound based on this information that you have here. We'll give you a moment to stop the video and try that. Okay, Let's go on to another variation on the same practice item, and we'll assume that everything remains the same except for one thing. Now what we want to do is compute the 99% confidence interval. Okay, so in using our t-in function, instead of putting in a probability of 0.05, we're now going to put in a probability of 0.01, and that's going to generate a 2.95 critical value, as contrasted with the 2.13 confidence interval that we had a moment ago. But the logic is still the same. Okay? And to remind you, you can plug those values into this formula, upper bound mean plus this quantity, and lower bound mean minus that quantity. So we'll let you go ahead and do that. Okay, so let's see if we can begin to summarize what we've learned about confidence intervals. Researchers can make their error bars equal to confidence intervals instead of standard deviations or standard errors or ranges or interquartile ranges. We're giving you lots of different tools for describing the variability that you might have in your data set. The researchers might then say, we are 95% confident that the population mean falls between the upper bound and the lower bound. And we got some practice in this video computing the upper and lower bounds. Larger confidence levels have larger confidence intervals. Again, the confidence levels might typically be something like 95% or 99%, and 99% confidence will typically have a much larger distance between the lower bound and the upper bound relative to, say, the 95% confidence level. Okay, we'll let you stop the video one more time before we proceed to effect size. Okay, welcome back. And we'll start our conversation on effect size. And we'll begin this with what I think is a fun mantra, and that is, there is trouble in paradise. Can you say that with me? There is trouble in paradise? There you go. Okay. And the paradise that I'm speaking of is this null hypothesis testing that we've been doing in the last few weeks. We've been talking about coming to a determination about whether a particular score is significantly different from some other score or some reference value. We've been talking about statistical significance. So one major problem with null hypothesis testing, or inferential statistics, where we're trying to come to a conclusion about statistical significance, is that the outcome depends on sample size. For example, a particular set of scores might generate a non-significant t-test with a sample equaling 10. But if the exact same numbers were duplicated, and now we have n equals 20, the t-test suddenly could become significant. So to appreciate this point, I'd like you to consider the possibility that you might have run a particular study that was of interest to you, and you had 20 people. And you got your results, you put them all together, and you went off to a conference to report that you have a statistically significant effect of your independent variable. Okay? Now, interestingly, in this hypothetical, you might be standing next to somebody who also has a poster at this conference, and they ran, just by chance, exactly the same kind of a study, with 10 people, though, rather than 20. And when they ran 10 people, what they found was they did not have statistical significance, whereas you ran 20 people and did find statistical significance. So with that as context, imagine that I walk up to the two of you, and I see that these two posters are essentially identical to each other in all ways, except for their sample size and their conclusions. The person with 20 participants is telling me that they have a statistically significant finding. A person with 10 is telling me that they don't have a statistically significant finding. It's difficult for me as a consumer of that information to try to figure out whether I should be impressed by the influence that this IV might be having on the DV, the independent variable on the dependent variable. Okay? So this brings us to the issue of effect size. Effect size can be defined as the magnitude of the influence that the IV has on the DV. Effect size does not depend on sample size. And this is really good news. I say here jokingly that there was much rejoicing. Once we've moved to an analysis of effect size, we no longer have to depend on sample size. Yes, it might be true that you and the person next to you come to different conclusions about statistical significance, and that difference might be driven entirely by sample size. But if we were to run an effect size analysis, we might see that the two different posters come to exactly the same conclusion about the magnitude of the influence that the IV has on the DV. And to do this, we need some kind of indicator of effect size. And we'll be learning about different types of effect size indicators. The first one that we're going to introduce is something called Cohen's d. And here's the formula that we have, d for Cohen's d, and this is referring to the size of a difference, by the way. It's one of the ways of thinking about this. What kind of a difference does your independent variable make? The formula is 2 times the observed value of t from your study divided by the degrees of freedom that you have in the study. And Cohen was good enough to give us some ways to think about the different values that you might obtain. And this is actually very dependent on context. In some subfields of psychology, these numbers are very helpful. In others, these numbers are less helpful. But just to help us in this particular course, I would like you to memorize these particular values from Cohen's d. If you get a Cohen's d value that's smaller than 0.2, we would say that's indeed a small effect size. It's not a very large impact that your IV is having on your DV. If you get a Cohen's d value between 0.2 and 0.5, we might say that you have a small to medium effect size. If it's between 0.5 and 0.8, we might say that you have a medium to large effect size. And if it's greater than 0.8, we might say that you have a large effect size. That there's really a very strong influence of the IV, or independent variable, on the DV. Okay. A statistically significant effect is said to be a reliable effect. And when we're using that phrase, a reliable effect, that is to say that it would be found repeatedly if the sample size were sufficient. Okay, we would get that time and time again. And maybe not every single time, but it would be there relatively reliably. Statistically significant effects are not likely due to chance, and we can always specify the probability that we did find a significant effect just by chance. That's what our alpha level is. And scientists are very careful about making these kinds of errors, and we actually like to quantify the probability of making these errors. That's why we put so much weight on the alpha level, the 0.05 standard in our science. An effect size, or an effect, can be statistically significant, yet puny. Okay? That is to say, it might be the case that we have something that recurs reliably, but it's not a very meaningful or important kind of difference, even if it is occurring somewhat reliably. So this is the distinction between what we might call statistical significance versus practical significance. For those of you who have clinical aspirations, it's certainly true that you'd want to know how reliable a particular effect is, but you'd also want to know something about the magnitude of its influence in a clinical setting. So this, again, is the distinction between statistical significance versus practical significance. And the effect size can help us more with this idea of practical significance, whereas an analysis of the alpha levels helps us more with statistical significance. So there are different kinds of examples we can give here. Just to give you one example in this video, and then we can talk about others in class, I'll give you the analogy of a roulette wheel, and it can have an effect that is small but reliable. Some of us are familiar with roulette wheels that you might see in a casino. Typically, it might have something like 38 different slots. This would be a spinning device that has 38 different slots, and a small ball will roll around and land in one of those slots on a given roll of the roulette wheel. Okay, so what will happen then is we can typically bet on either maybe the odd numbers or the even numbers. We might have the odd numbers shown in red, and we might have the even numbers shown in black, and you're betting red and black on any given roll. Typically, you would say that that's going to be a 50-50 trade-off, that you've got a 50% chance of winning money, 50% chance of losing money, and this would be actually a very boring game to play. Half of the time you give your money over to the casino, half of the time they're giving it over to you. Nobody's making money or losing money. But on a real roulette wheel, there are actually some departures from this strict red-black alternation. There are 2 slots, frequently 0 and 00, that are painted green rather than red or black. And that's a relatively small proportion out of the something like 38 or maybe 40 slots that you're going to have on a roulette wheel. But every so often, that ball will land in one of these green slots. And if that happens, and you've bet either red or black, you're going to lose your money. So this now works out to something like 1 out of 38, and this might be approximately between 5 and 6% of the time. You're not going to win by betting on red and black. You're going to lose that money to the casino. So instead of it being 50-50, it's now something more like maybe 56-44. That's not a really big difference. On most rolls, you really are just exchanging with the casino, but there is a small but reliable effect. And that's the theme that we have throughout the different examples that we see here, and we can develop those further in class. Okay, why don't we move to a couple of potential pop quiz questions. Using 2 sentences, generate your own novel example of something called a meta-analysis, and if you like, here's the meta-analysis wiki page that you can copy and paste to see how you might begin to respond to this question. Then, we'll see if you can also do this potential pop quiz question. In your own words, explain how Cohen's d can be helpful in a meta-analysis. We'll give you a moment to stop the video. and then we'll proceed to some final thoughts on independent groups designs. We've introduced these before and we've talked about them in class. We'll start out with this very nice diagram about independent group designs, and we'll ask the question about how the different groups in our research design have been formed. We'll start out with maybe the most obvious kind, and then we'll come back to the one that's new for us. Okay? Let's start out with a random assignment. We've talked a lot about experiments and the importance of having random assignment to get people distributed to our different experimental conditions. We would call this a random groups design, and we can use a purely random mechanism like a spin of the F9 key in Excel. Using the equals rand command would be one of the ways of doing this. We can use a random number table to assign people to the different groups. We can use block randomization as well. On the other extreme, we can let the groups be formed, if you will, by nature. We might call this a natural groups design. And here we might want to be comparing groups that differ from each other before they came into our study. This might be athletes versus non-athletes. It might be college graduates versus those who didn't graduate from college. It might be folks of different gender. It might be folks from different kinds of backgrounds. It might be folks who have different kinds of clinical conditions. Whatever those naturally occurring groups are, they're not randomly assigned by you and me. But this too would be a type of independent groups design. We would still be interested in how these groups differ from each other. Now we'll introduce a type of design that we haven't talked about before called the matched group design. Now this is interesting because it's a little bit like the random assignment condition in the sense that you are forming this group, it is not formed by nature. On the other hand, what we're doing is we're departing very strongly from a pure random assignment. What we're doing instead is we're taking something like a pretest on the variable of interest, typically the dependent variable, and we're going to try to match two groups before we invoke our treatment. So it might be the case, for example, that we're interested in depression. And we might have 100 people who are going to be in our study. 50 of them will get our drug, 50 of them will get a placebo. Okay? What we'd like to do is make sure that before we start, the mood levels in the one group are roughly the same as the mood levels in the other group. And to do this, we can give everybody a pretest, maybe something like the Beck Depression Inventory, and we could get the scores for each of the 100 people, and we'll take some folks with really, really low scores, and we'll put some of them into the control group, we'll put some of them into the experimental group. We'll take another subset of those folks who have intermediate scores, and we'll distribute them evenly between the two groups, and we'll take the folks who have the highest scores as well and distribute those evenly to the two groups. So this is nice because it gives us some kind of equality before we begin to impose our experimental manipulation. And we're now not allowing random assignment to perhaps create an imbalance where we have maybe very high scores in one group and very low scores in another group. Instead, what we do is we're grabbing the bull by the horns and we're trying to equate the two groups using some kind of pretest measure, typically on a variable of interest, very often the dependent variable. Okay, so now with that, we'll begin to wrap up by going to a total of 4 different potential pop quiz questions. I'll read each of these, and then as you are wrapping up for today, you can respond to these and bring your answers to class. Here's the first potential pop quiz question. As we've seen, inferential statistics can address the issue of reliability. Statistically significant effects are said to be reliable effects. What is the ultimate test of an experiment's reliability? And we'd like a one-word answer here. I'll give you a hint. We've talked about that one word earlier in today's presentation. Let's go on to our second potential pop quiz question. In your own words, explain what a conceptual replication is. Use an example of your own or one from our readings. Okay, 2 more and we're done. Here we go. The next potential pop quiz question. In your own words, explain what a matched group design is and when it can be advantageously used. And if you are watching the earlier portion of this video, I've given you an example that might be helpful to you. Finally, why don't we end this way? As we've noted many times, the scientific method has 4 goals. Which goal or goal can be met by a natural groups design and which cannot? Okay? Explain your reasoning. So we'll give you the opportunity to respond to those questions, and more generally we'll ask you to report, as you typically do, what has been clear and what has not been so clear throughout this presentation. I look forward to seeing you in class.